Next speaker is Sally Hicks from the University of Dallas. And Sally, if you can hear us, please.
I can. Can you hear me?
Yeah, we can hear you, but we cannot see you. We can see your slides as well, so please go on, Sally.
Okay. First of all, I would like to thank Nico for inviting me, and just to say that I love the title of the conference, and so my title for my talk is really a play on the conference title, because Tellurium-130 has this sort of wealth of things spilling forth from it as far as nuclear structure is concerned, which reminds me much of Cornucopia, which we use for as an emblem of our most recent holiday here in the United States. I am a teacher of undergraduate students, and most of the information that I'll be presenting today was analyzed by undergraduate students. And I am hoping that I can address some of Nico's undergraduate students in South Africa as I give my talk. Why study Tellurium-130? Well, it's one of the candidates for neutrinoless double beta decay, because you have to have a double beta decay to get to xenon-130. It's also part of a very comprehensive nuclear structure study that we've done with Jeff Van Hoy from the Naval Academy, Steve Yates at the University of Kentucky, and my group at the University of Dallas, where we've looked at the stable and quasi-stable tellurium isotopes ranging from 120 to 130 tellurium. And quite interestingly, 2 of these tellurium isotopes are actually neutrinoless double beta decay candidates. 130 tellurium historically has been quite important in double beta decay studies. It's the first nucleus in which normal double beta decay was observed, and that was done in 1950 using geochemical methods by Inghram and Reynolds. They published their published value of the half-life was 1.4 times 10 to the 21st years, which really doesn't differ a great deal from our current best value. If you look at the isobar parabola for A = 130, you can see that Tellurium-130 cannot decay by a single beta decay to iodine-130, but to get to the lowest mass in this isobar chain, you have to have a double beta decay. After Maharana came forward with the idea that a particle could be its own antiparticle, the neutrinoless double beta decay was proposed. And in this process, when the 2 electrons are emitted in the 2 antineutrinos, the antineutrinos would annihilate. And this is an example where lepton number is not conserved, so it's a violation of the standard model. And so this is some very interesting fundamental physics. If this is observed, then this would tell us that the neutrino is its own antiparticle, and it would also allow us to deduce properties of the neutrino, including the neutrino mass. So Tellurium-130 is a particularly good candidate for neutrinoless double beta decay. It has the highest natural abundance of any of the neutrinoless double beta decay candidates of 34%. It has a high Q value, which implies the half-life might be short, at least relatively speaking, for neutrinoless double beta decay candidates, which might make it easier to identify. There are a couple of very major experimental efforts looking for neutrinoless double beta decay in 130. One is CUORE at Gran Sasso in Italy, and the other is SNOW+ in Sudbury. One looks at the heat produced in the double beta decay, the neutrinoless double beta decay process, and in this detector, tellurium oxide is actually what is used as the bolimeter, and it can be made extremely radio pure and have a good energy resolution. And already measurements that have been done at Gran Sasso have shown that the lower limit on the lifetime for this double beta decay process is 4 times 10 to the 24th years to 90% confidence level. The detector at SNOW+ actually looks at scintillation. This one looks at the heat produced. Both of these are very high dollar experiments, which are also looking for evidence of dark matter. Steve Yates showed this slide earlier, but I just want to reiterate, especially for the students' sakes, why this is so important. Even if these major experiments can measure this half-life extremely well, you still have to know quite a lot until you can get valuable information about the neutrino mass. So the nuclear matrix element, which connects the parent nucleus to the daughter, is shown right here. It goes into this expression squared. And here are the theoretical calculations. Steve talked about them for the germanium nuclei, but it's even worse when you get to tellurium or to the mass 130s. you can see there's a large range in the theoretical values for this nuclear matrix element. Now, we certainly can't measure that matrix element exactly, but what we can do, and this is where the contributions from our measurements at the University of Kentucky come into play, is we hope that by understanding the structure of tellurium-130 much better and the structure of xenon-130, then there's hope of improving the uncertainty in these nuclear matrix elements connecting the two nuclei. Right now, Aaron Peters is working on analyzing xenon-130, and I'm working on 130 tellurium. We actually did these measurements several years ago when we were trying to look for mixed symmetry states, and we realized we have all this wealth of information at higher excitation energies. Now, following Paul, I don't even know if I want to talk about this slide, but when we look at the underlying structure of the stable tellurium nuclei, historically, one of the markers that we've used is look at the ratio of the 4-1 plus to the 2-1 plus. And here I've plotted this ratio across the tellurium isotopes from 110 at least to 140. Here are the stable ones or the quasi-stable ones in red. Here's the neutron midshell. Here's where you have semi-magic tellurium-134. This value is very consistently at 2 as you go across this isotopic chain until you get to 130 where it drops to just slightly below 2. So when you look at this ratio, of course, we're looking at the nucleus as a vibrator or a rotator, which Paul just told us couldn't happen, but historically we've looked at it this way, so just go along with me. So as we look at the 0 phonon, 1 phonon, and 2 phonon states, then we expect this ratio to be 2 for a vibrator. So it looks like we have good vibrational nuclei, and then going into maybe a shell model nucleus as we get to 130. If we look at the BE2 values, these are certainly telling us very valuable structural information. If we have a 2 phonon state, for example, a 4 plus decay into the 2-1 plus, we would expect to have a large BE2 value, which is twice the decay from the 2-1 plus to the 0-1 plus. If we look at the low-lying positive parity states in these nuclei, and here I've just circled a region, I think Paul alluded to some of these earlier, is that if you look at tellurium-120 and 122, these are historically been called good examples of 2 phonon excitations. They're in textbooks, for example, as examples of vibrational nuclei. If you start to gaze outside of this red circle, you can see that there's some other things going on. A study by Pascu et al. Looking at the BE2 values for the 2-1 plus to the Z1 plus found that all this could be explained very well using the IBA within the U5 limit. So they, in that study, they looked at the low-lying properties as well as the 2 neutron separation energies and concluded that the telluriums were all very good examples of U5 nuclei. But certainly, if you start to gaze out and look at higher levels, you see a wealth of things going on that can't be explained in terms of a simple vibrational picture. So to look at these higher lying levels in more detail, we've done a series of measurements using the NN prime gamma reaction. This work was done at the University of Kentucky. And I don't want to spend a lot of time on this because Steve gave so much information earlier, but we do use the PN reaction to produce neutrons. We scatter off a very large sample. We would like to have a large fraction of a mole. We can detect the gammas or the inelastically scattered neutrons. For our gamma ray spectroscopy, of course, we use the gamma rays, which are in many ways just a really nice way to look at the spectroscopy of a nucleus. So we use neutrons, and they're ideal in many respects because we have no Coulomb barrier to overcome. It's a non-selective interaction, so we see both positive and negative parity states with spins up to about 6. In tellurium-130, we actually see a few spin 7 states just because of the decay scheme and the higher lying levels have to go through here. This is, for tellurium-130, more than for the other telluriums we've studied, the fact that we see so many of spins and parities has been very nice because the higher lying work or the previous work has been predominantly beta decay, which is much more selective. We have good energy resolution and we're able to measure Doppler shifts. Specifically for tellurium-130, we had 50 grams of this stuff with a 99.5% enrichment. We measured excitation functions and gamma ray angular distributions to get level spins and parities, multiple mixing ratios, branching ratios, and Doppler shifts. What Steve didn't talk about, and I think the use of this coincidence, or the gamma-gamma coincidence measurements using what they call KEGS, the Kentucky Gamma Ray Spectrometer, I think this is actually the last experiment that was done using this gamma ray coincidence device. And I want to say just a little bit about it because it has been so beneficial in putting transitions in Tellurium-130, which has actually been quite complex because there's a lot of low energy gamma rays. So here we have the neutron comes in and scatters off or excites the sample. We see gamma rays coming from a cascade that will show that will come in a very small time window. So we're able to develop a coincidence matrix and then look at gates. This is just to help some of the students who may not have done this before. The coincidence measurements can be very beneficial. Here I have just a couple of coincidence gates, one on the 182, which is a decay from the 6-1 plus to the 4-1 plus, and then another gate I've set on the 5- to 4 plus. And here you see those two gates, you see a same energy gamma ray of 331 keV showing up in both of these. In the gates below, you wouldn't see anything, any difference here. But because we can have these higher lying gates, we're able to make a really clean placement of gamma rays in the level scheme. Here's the bread and butter of the measurements done at Kentucky, and that's using the Doppler shift attenuation method. Here, the 0 degrees is defined really by this dark blue detector location. We can move the detector around in the lab. So anything in this quadrant is going to be blue shifted. Anything back here will be red shifted. The gamma ray will, the Doppler shifted gamma ray undergoes, really goes along with a relationship that depends on the unshifted gamma ray energy. And then this factor F experimental, which is our Doppler shift attenuation factor, which really deals with the fact that our nucleus is recoiling through that 50-gram sample as it decays. And so we have to take into account all that interaction between the recoiling nucleus and the target material. And then we have a factor of the velocity center mass divided by C. This is of the recoiling nucleus, and then this is the cosine of the scattering angle. So you can see we get very nice Doppler shifts. We can take the slope of these lines, extract the experimental Doppler shift attenuation factor, compare it to Winterbond stopping theory. So this does in fact depend on the model we use to extract the lifetimes. Everything else is determined experimentally, and then we're able to extrapolate defined lifetimes. So we do this at Kentucky routinely, even on heavy mass nuclei. And this gives us lifetimes in the range of a few femtoseconds to a few picoseconds. And this is just a very valuable technique when we study nuclear structure. Here are some examples of gamma ray angular distributions. The shapes of the angular distributions when compared to statistical model calculations allow us to define the spins and parities of the states we're looking at. And here is just an example of how we extract the multipole mixing ratio. Here's an example of a 2,3 plus to 2,1 plus transition in which there are actually 2 allowed possibilities. These data were published previously in a study of mixed symmetry states in this nucleus. And that was a study we did where we really looked at states below about 2.5 MeV. So the whole idea here is we develop a level scheme that has the spins, parities, the branching ratios, etc. The big thing is that we get the reduced transition probabilities, mainly for M1, E1, E2, and then mixed transitions. Once this is done is really when the interesting physics starts to play a role. And so one of the things we were looking at, and I should say that this is very much a work in progress, and because I wanted to direct this to Nico's students, I really wanted to pull out examples of some collective structures we were looking at and then talk about some particle structures, which are actually pretty well described. As I try to develop band structures like Paul just presented for the ruthenium nuclei, I really still have some weak transitions that I have to try to place in the excitation scheme. So I just want to pull out a couple of things. And certainly the Tellurium nuclei, Tellurium-130 is shown here on this slide from Chris Haida and John Wood, looking at regions of the chart of the nuclides where shape coexistence has been seen. Tellurium-130 is here very close to this very rich cadmium 10 nucleus, or 10 region. And if you look at just comparing the cadmium nuclei with tellurium, cadmium with Z equal 48 has 2 proton holes in the G7 halves shell. If you excite 2 additional protons up here, you get a 2 particle 4 hole state, and that's has 4 active positive particles. And if you look at the tellurium nuclei, which starts with 2 protons up here in the G7 halves, exciting 2 additional particles, you would have a 4 particle 2 hole. So you have the same number of active particles. And so for students who may not be familiar with this, what happens then is, I mean, normally you would have a lot of energy when you have an excitation across a major shell like this. But because you have all these active positive particles, when you have a lot of active neutrons, which you would have at mid-shell at n equals 66, then you would expect these excitations are actually pulled down low in energy, even though they are coming from the excitation of some particles across a major shell gap. They're pulled down low in energy, and in fact, in the cadmium nuclei, there's a clear signature of these rotational bands, sort of a band of rotational levels built on these intruder excitations. And so these are all seen very clearly in the cadmium nuclei and in the tin nuclei. And so because tellurium has the same number of active particles, we're looking for this same type of shape coexistence in the tellurium nuclei. So one of the first indicators is to look at the 0+, and certainly when you get away from the tellurium 122, you're starting to see the 0+ go up in energy. In fact, if you consider shape coexistence to be exhibited by these V-shaped structures, if you look at the 0.2+ levels across this isotopic chain, or you look at the 0.3+, they both kind of have a V-shaped structure, and the same is true of some of the 2+ and 4+ levels. But the real indicator of shape coexistence is not just how the energies are behaving, but you have to look at the BE2 values connecting the various states. And so this is borrowing a picture from Paul's work where he looked at the cadmium and started to compare the tellurium. These tellurium 122 and 124 are some results from our work, but he started to put these BE2 values and you can see that you're seeing values similar to what's seen in cadmium. When we get to 126 and 128, we weren't able to deduce the lifetimes for these 0+ states. But where we are in 130 is I've actually identified 3 0+ states in tellurium 130. I'm able to find the lifetimes. And so all of these are possible candidates, but at this point, I am still trying to identify transitions that would go into these and be indicative of some type of band structure. I certainly have some candidates for a decay into the 1964. When you do coincidence measurements on a natural sample, you do get a wealth of information, and it's you have to be very careful to make sure your gates are telling you what you think they are. So the jury is out here. I mean, I think that there is evidence of shape coexistence in tellurium 130. I don't think it's as clear as in the cadmium nuclei, but there are not nearly as many measurements made on these tellurium nuclei as has been done on cadmium. I think there's a lot of room for more experimental work. All right, so let me move to a couple of particle type excitations that I think we understand very well in these nuclei. And if you look at the lowest 6.1+ across this isotopic chain, and we just it was tentatively assigned in tellurium 130, but the lowest 6.1+ state in 130 is consistent with the others. It's actually very constant in energy. So if this were a 3-phonon state, so this is a deviation away from a sort of a vibrational picture, because if this was a 3-phonon state, then you would expect it to have this sort of parabolic dependence, just like the 2.1 you see in this 2.1+ as you go from mid-shell to closed shell. But in fact, that 6.1+ is very constant in energy. If you look at these 2 proton particles, these 2 G7 particles coupled together can form a 0+, 2+, 4+, or 6+ state. And a particle excitation, in fact, might be more constant in energy because the 2 protons are the same for all the tellurium isotopes. For all the students involved, you are not allowed to have the 1+, 3+, or 5+ because of the Pauli exclusion principle excludes those. Just yesterday, there was a publication that caused me to change this slide. I was showing that in tellurium 134, which is actually a semi-magic nucleus, these 2+, 4+, and 6+ excited levels were not very collective and seemed to be very shell model in origin. A paper that came out just yesterday by H. Wang et al. shows their shell model calculations indicating that yes, these lowest states in 134 are actually very well described as these 2 proton excitations. And so this essentially is staying constant as you go across the tellurium isotopic chain, that 6+ excitation is a 2 proton excitation, and you're not seeing the vibrational contribution that you would expect with a vibrational nucleus. If you go to negative parity excitations, here the negative parity excitations, when you get away from 130, are caused most easily by looking at the shell model again. Notice the negative parity excitations, the lowest one is a 5-, the next one is a 7- across this isotopic chain. They behave very differently than the positive parity excitations in that they are falling off as you go toward closed shell. But you can describe these, the 5-, which is the lowest, is described as a promotion of a neutron from the 3s1/2 shell up to the H11/2. So you have a particle hole configuration leading to this 5- state, and the 7- is caused by the promotion of the D3/2 up. Now, how we feel comfortable in saying that is if you look at single particle excitations in the odd mass nuclei, then what you see, if you look at the lowest 11.5- state, it falls off in energy just like these 5- and 7- do. So the general falling off in energy is thought to be due from the H11/2 particle. And then the distinction between the 7- being due to this and the 5-, which could actually also have some of this component, but it's predominantly the S1/2, is shown, a slide which was shown originally by Carrick in 1971 paper, where just a few of the 5- were shown. But as you extend this across a greater portion of the tellurium nuclei, if you take the difference in the 7- energy and the 5-, you see it falls like this. And then if you look at the 3/2+ excitations and the 1/2+ excitations in the odd mass tellurium and take the difference in those, they are falling off in exactly the same way. So this really supports the idea that the 5- is from the coupling of the 1/2 and the 7- is from the coupling of the 3/2, and that these are just particle hole excitations. One of the ways this shows up experimentally, which we find is very interesting and shows that tellurium-130 is becoming very much more shell model-like, is if you look at decays of the negative parity states. I just plotted them for 124. In 124 tellurium, the negative parity states go to a lot of positive parity states, so you have a lot of mixing of various things going on. But when you get to tellurium-130, all the negative parity states are decaying to negative parity states, and they all go through the 5-. And so when you look at the excitation function of the 5-, it just goes through the roof just almost instantly because of the feeding from all the other decays above it. And the 7- is seen here because there's a lot of decays into that 7- as well. So you're really seeing a kind of a purity in the type of excitation, I think, when you get to 130 compared to the lower mass tellurium nuclei. And someone, I try to put these things in band structures and start talking in the way that Paul does, but I'm certainly not there yet. And so I would just say that the 3-, which somebody just mentioned, and the octopole excitations, if you look back to some earlier, I should say the 3- are more interesting because they do decay outside of the negative parity bands. But if you look at some PP prime scattering from 1975, you can see that in this nucleus, the lowest 3- state is actually at 2527. And so there's a pretty good indication that it has a lot of particle configuration, and maybe the octopole collective strength is showing up a little bit higher in energy, because in the proton scattering data, the 3- is showing up at the higher energy excitations, but it's really buried by this doublet here at 2.46, which is a different parity excitation. It's barely showing up in the protons scattering at all. So let me go then to some conclusions, because we were talking about this in terms of neutrinoless double beta decay, and one of the reasons the structure is important. The structure is really complicated in tellurium-130. I pulled out some things that we could describe, but developing a structure like Paul was showing with respect to ruthenium has actually been quite complex. So we're still working on that. Aaron is finding the same kind of thing in xenon-130. It's a very complicated level scheme, a lot of low energy transitions, which are always hard to to place confidently in a scheme, even with coincidence data. So what we're suggesting from this is that there's still a lot of work to be done. I think a lot of different kinds of measurements need to be done before we can think that we have a way to confidently extract the nuclear matrix element linking Tellurium-130 to Xenon-130 and have any hope of extracting a mass for the neutrinos with some confidence, even if we get this half-life. So Tellurium-130 tends to be a transitional nucleus, not from vibrational to rotational, but it shows some clear signs of shell structures. And I just want to say, I hope you enjoy this nuclear taste of nuclear physics in Tellurium-130. And then I want to acknowledge all the people that have worked with us. Again, Jeff and I both work only with undergraduate students, but we do have a series of wonderful people who helped us with these tellurium measurements through Steve Yates' group at the University of Kentucky. Thank you.
Thank you, Sally. I'm doing my job to thank him. Thanks. So questions, and I think, so we have a question from Philip Adsley. It asks whether is it possible to extract cross-sections to particular states, and can that tell you anything about shape coexistence in tellurium isotopes?
Unfortunately, we didn't do anything to normalize this when we weren't even thinking about shape coexistence, I don't think, very much when we started. I mean, we started these projects a long time ago where we were really just trying to look at the evolution of structures across the tellurium isotopes. So we do sometimes measure cross sections by also doing measurements on iron or something like that simultaneously. We did not do that with the tellurium nuclei. So I think the only information we could give would be relative.
I have a question. I understand that these measurements are made in order to test theories and also thinking about double beta decay. Which are the observables from experiments which are the most important for the theories to be able to reproduce? Oh, I mean, none of the theories can reproduce everything. That's what I mean.
Right, but the thing that really distinguishes the theories are the lifetimes, which we do very well, I think, for a wide range of nuclei in these gamma ray spectroscopy measurements. Certainly it's the lifetimes, because you can find many levels. If you start doing calculations, you can find levels that do about the same level of quality describing energy levels, but the transition rates are really what tell you something. And so that is why the measurements at Kentucky are so valuable. It's just that the Doppler shift attenuation factor gives us not just a couple, like if you look in the nuclear data sheets about what's known for 130, there's only a couple of lifetimes that are known. And so I probably have lifetimes for 50 or 60 states from here that, you know, I now have to process and try to compare to theories and some other work. You know, I mean, I'm just analyzing this right now. And so what I find is I read papers, it gives me something else to look for. When you work with undergrad students, you don't always hand off things, you have to do them yourself. And so, you know, I'm looking for these different types of things as I read papers. And it's just, it really is the lifetimes that give you the information.
Thank you, very nice work. So I don't see any other questions in the chat. Anyone has a question? So I thank all of the speakers in this session so far. And I don't know whether, Nico, you want to say something or you want me to say something that we have to be back at 7 p.m. according South African time for a very epic talk.
To thank all the speakers again. Thank you so much, Steve and Paul and Sally. This is the old Kentucky crew, and I really love them very much. And you know, these three guys are very hardworking. When you go to do an experiment to Kentucky, Sally and Jeff, they come and they spend there 2 people running the accelerator, getting the data. Sometimes we may help them, but they are running the show themselves most of the time. It's an example for me, Sally, to always see you working so hard, and also Paul and Steve, obviously. Thank you very much. And also, Zsolt, for you to stay until the longest sharing session. I think we should give it a break. I'm going to show John Wood's video because we're going to have he's going to present the keynote speaker, and I'm going to be the actual presenter. So after 3 talks already that we gave in these 2 days, the 4th one is probably the toughest one, because it's just a longer talk. I'm already tired. I was working with Kenzo until 3 o'clock in the morning. So, but let's hope that things go well. And let me just show quickly. Let me share the screen if I can. Joel, are you okay with that?
Yeah, it's yours. I just want everyone back at 7 o'clock.
Excellent, excellent.